can start now.
Okay. So I'm Tony Phillips. I'm a professor emeritus now. I taught my last class just a year ago this spring, and I'm still working on things. The sphere inversion is something that I've been working with really my whole academic life, because I wrote an article about it in 1966, which is probably before your parents were born. So it's something that's been going on. And I'm always looking at new ways of explaining it. So today I'm sort of experimenting with a new twist on a presentation. So I'm going to borrow from a talk I gave, let's see, year and a half, 2 years ago at Jeff Cheeger's birthday birthday celebration in Shanghai. And but I'm going to run it backwards, so we'll see what happens. Also, I'm going to come on, let's go, baby. Yeah, I'm going to skip a lot of the background material. It's pretty easily accessible if you're interested, or I can ask if you have a kind of a mathematical question to ask. You can ask it, and I'll try to make time to answer it. But I'm trying to just give the the crux of the construction and leave out a lot of the periphery. Okay, so here's the problem: how to turn a sphere inside out. What does this mean? Well, we have a blue sphere. This is just the surface, right? It's empty, but the inside of it is painted red. So if you were to make a hole in it like this, and you look inside, you'd see red. What you would like to do is turn it inside out. Okay, well, how do you do that? Well, if you could make a hole in it, it would be easy, because you would just sort of pull it out through the hole. But without a hole, how can you do it? So there's some kind of rules that we have to follow here. The surface is allowed to pass through itself. Clearly, if you can't let the surface pass through itself, then you're stuck with what it is. It'll always be blue. But if you can let it pass through itself, then a little bit of the red inside can poke out on either side, right? You just imagine pushing 2 fingers across, and then out through the blue, the red will poke out. Okay, so the surface is allowed to pass through itself, but you're not allowed to have any creases like this. This is not allowed, no creases. Right, technically speaking, you can't have any, the surface has to have a tangent plane at every point, and at every point during the deformation. Okay, otherwise you could turn the sphere inside out like this. You could go from here to there just by poking out 2 fingers, and then keep pulling that little knurl tighter and tighter until it just vanishes. And then you'd have a red sphere. Except all along here, right, you'd have points where you'd have creases. So this is not allowed. So how do we do it? Well, it turns out to be pretty involved, because in the space of maps of the sphere into 3 space that satisfy, they're allowed to self-intersect, but they have to have a tangent plane at each point. So we call those immersions. Of S2 in R3. So you can imagine making this into a space by saying like 2 immersions are close if they're right. You're thinking of now as maps from S2 into R3. Now I'm getting technical, which I promise not to do. But in any case, what I wanted to say is that suppose we could suppose this such a space makes sense, then the blue map and the red map are very far apart. You have to go through a long journey in the space of immersions to get from one to the other. So we're going to be taking that trip today. So this is all stuff about immersions, which I'm going to skip. So it really boils down to this. You look at this little piece of surface here, right? I have, I'm switching now. I have a yellow sphere turning into a green sphere. Okay, I wanted to do that before, but the yellow didn't show up well on the screen, so I used red and blue. So this gizmo, it doesn't really have a name. It turns out that it can be turned inside out in R3, keeping the top and the bottom at their original levels. So essentially only by planar moves. You can imagine sliding. We're going to be, this surface, in case you can't see it well, there's two saddle points, a yellow saddle point and then a green saddle point over it. And the edges of the saddle points are connected by ribbons, as you see there on the screen. So that's what this thing is. And it lies between two heights, say, in R3. And the whole point is that you can turn it inside out, keeping the top and the bottom exactly at the same height that they started out with. So everything is kind of a planar routine, planar deformation, which gives this particular inversion scheme an advantage over the others, because our minds aren't really built to deal with three-dimensional deformations. They're very hard, but things that are just happening in the plane, we're well equipped to process. Okay, so I'm going to turn this thing inside out, keeping the top and the bottom at their original levels. Now, let me just add a little parenthesis here. You can't do this. Come on. You can't do this with a cylinder, say. So imagine you had a cylinder and it was yellow on the outside and green on the inside. And you wanted to turn it into a cylinder that's green on the outside and yellow on the inside without keeping the top at the same level that it starts and the bottom at the same level that it starts. Okay, this can't be done because if you were to orient this boundary, by the time it got to be green outside, the boundary would be going the other way around. And there's no way of getting a curve, keeping it nice and smooth with tangents. It can intersect itself, but there's no way of deforming a curve to one going the opposite way without introducing cusps or singularities. That's an old theorem that goes back to Whitney and Graustein. Okay, so you can't do it with a cylinder, but you can do it with this thing. But it takes some work, so you're gonna have to be patient. Let me just jump to the end and show you how this is how turning the gizmo inside out will allow us to turn the sphere inside out. So the gizmo is really a sphere with 4 disks missing. And the 4 disks are attached, 2 on the top and 2 on the bottom. There's a green disk at the upper. This would be a green disk. This would be a yellow disk. Right, it's yellow, but the green is poking through. And on the bottom, you have a green and a yellow. Okay, and if you continue if you look at the whole of those disks, you get a surface like this, right? I have the Gizmo, and then I have the 4 disks attached, 2 on the top and 2 on the bottom, a green, a yellow, and a green. And they've come together to give you the image of a map of the sphere into 3 space that's nice and smooth. And you can see how by kind of pushing this guy down, right, you can make it into a green sphere with a yellow ribbon, with a yellow knurl going all around it. And then you can deform that to a yellow sphere. So this is actually not too far away from the yellow sphere that we start with. Okay, so there's a that's the first step. And here's some steps. How would you get to it? You start with a yellow sphere, and then you start pushing it through, and then 2 green fingers pop out. And then you kind of deform these fingers. You mush them around, push one up, twist them around, so that you finally get a configuration like this. It should be fairly plausible that this thing, even though it's unusual, is actually can be deformed back to be a yellow sphere without too much effort. Again, any questions, just sing out, or I can't see the chat thing because I don't know how to make the doc go away. Anyway, just sing out, okay? So here we are. Suppose we're able to turn this thing inside out. Okay, so here it is, and here it is inside out. Okay, then if the inside out one would be completed to a sphere also in exactly the same way, but this one, when you undid that original process, you'd end up with a green sphere. Okay, so this is how you're going to get from a yellow sphere to a green sphere. Take a yellow sphere, make it into this weird thing, turn the Gizmo inside out. It turns out it's not totally obvious, but it's fairly elementary that once you can turn this inside out, those 4 disks can track along, and they end up in this position here. The yellow disk, the green disk on the top, the yellow disk and the green disk on the bottom. And you have your whole sphere. And now it's actually a green sphere when you undo the original homotopy. Okay, so that's the context. And here we go with turning the Gizmo inside out. I'll start this unless there's any questions about why am I doing this? Okay, you were warned. So on the next few slides, it's always going to be 2 images, one a before and one an after of each step, right? And so the after of this slide will be repeated as the before of the next slide, so everyone can see what's happening. And what I'm going to do is use this highlighter to bring out the elements that are actually moving. Usually a lot of stuff stays fixed and only some of it moves. That's the way I've organized the explanation of how, I mean, it could be done much more compactly, but it would be much harder to understand. So for example, the first thing I do is I take this top saddle point, and I just slide it in the same plane away from the bottom one. Okay, so as it slides, it sort of drags the ribbons along with it, sort of like a frog hopping forward. Okay, now at the top now is the bottom from the last slide. And what I'm going to do is I want to turn this saddle point around 180 degrees. And in order to do that intelligibly, I need to make some space by moving some of the ribbons around. Okay, so the first thing I do is I take this ribbon here, right, and I move it over here. Okay, that's not too painful. I just slide it across. Remember, the surface is allowed to intersect itself. Okay, now here's where it was. And the next thing I do is, what do I do here? I take this ribbon here, that's coming from this other side here, right? And I pull it across so it goes like this. Okay, so what I'm doing is this little loop here is sliding over to this position here. So the loop is still, that loop is conserved, it's over here now. And this piece of ribbon has moved over to here. Okay, I continue with this kind of thing. Actually, now I can start rotating the my upper saddle point. So it starts in this orientation. Here I've turned it 45 degrees. Nothing else has happened in the picture you can see. So the only change here is this is rotated 45 degrees. Then I rotate it another 45 degrees. Again, since I've moved the ribbons out of the way, the saddle point can rotate without any obstruction. Okay, now it's this way. I move it another 45 degrees, right? And again, everything just tracks along. It drags, like this ribbon here gets dragged around like this when the saddle point turns. And all the other ribbons just stretch or compress to allow this motion of the saddle point. And then one last step of rotation, it's it's gone that far, and now it's gone 180 degrees. Okay, so the saddle point has rotated 180 degrees, and now the ribbons are stretched all over the place. And I'm going to have to spend the rest of my energy putting the ribbons back where they in a place which will be useful for us. Okay, so what I've done is I started with the original two saddle points. I moved one up and I rotated it 180 degrees. Okay, this rotation is essential. All the sphere deformations, there are many different ones that have been developed over the last 50 years, but they all involve a 360-degree rotation of one thing with one part of the sphere with respect to the other. That's actually what makes them so far apart in immersion space. So this is only 180 degrees. We'll see that this is only the first half, but this is important. Okay, so now what we do is we start reorganizing the ribbons. So the first thing I do is I take this ribbon here. It was going around the bottom and up to the upper right-hand arm of the green saddle, and I pull it across. So these two intersections are going to disappear, and it's just going to look like this. Okay, when I pull, I take this piece here and I pull it all the way up to here, right? As I do that, these two intersections go away, and I just have a non-self-intersecting piece of ribbon going from this arm of the yellow saddle point to this arm of the green saddle point. Okay. The next step is I'm going to take, what do I do here? Hang on a second. What's going on here? It looks like I'm just moving the one that goes here. Okay, I'm just sliding it up. Right, there's nothing really happening except it's just being repositioned. Right, I slide it up in this direction so that it comes, this green comes outside that yellow, and it intersects. We have a little triple intersection point here, right? And this intersection point goes up. This intersection point actually slides along to go there. Okay. Now what do I do? I'm going to work with this ribbon here that goes from this arm of the green to this arm of the yellow. And I'm going to push it up so that it intersects itself and looks like this. Okay, when I push this up like this in this direction, it's going to form a self-intersection loop here, right? But the rest of it just tracks along and looks like this. I'm just sliding it up. So this is all sliding ribbons. Okay, what am I going to do here? Well, I take the ribbon that goes from here to here, and I just stretch it down in this direction so that it now goes all the way down inside that bigger loop. Whoa, what's happening here? Wait a second. Yeah, I'm doing more than that. So I'm taking this whole part here. So it joins this arm of the green to this arm of the yellow. Okay, and I'm gonna move it so that it goes all the way around like this. Okay, so it still joins that arm of the green to that arm of the yellow. And instead of just having a little loop here, it's just dragged down so that the loop has moved over to this this point here, and this ribbon that sort of went around here goes all the way, goes outside, sort of halfway around the top. Okay, some more ribbon work. This time, oh, actually, I've done enough ribbon work. So now what I'm going to do is I slide the green saddle point down over, back where it was first, over the yellow. Okay, so I didn't really have to slide it out. I could have done all the work with moving one saddle point on top of the other one, but as you can imagine, the pictures would have been more complicated. Okay, so I slide it back down again. I'm not quite where I need to be. Let's see. Here I've slid it down, and now I'm going to improve these ribbons just a little bit by taking this part here. This guy here is going inside and then outside. Okay, and I'm going to move him to go outside right away and then stay outside. That's the only change. So I'm just sliding this piece of ribbon here, just sliding it out away from the others. Okay, I think I'm almost where I want to be. The last thing I do is I take this ribbon here, it's going around like this, right? And I slide it in so that it intersects this way. So I move it in, I move this guy inside this guy. Okay, and but that's all that happens. Okay, so I've done a lot of work, but now you can see there's a very interesting configuration here, because at each point you have two yellows are facing. Right, if you look everywhere, there's a yellow piece of surface facing another yellow piece of surface. Right, does everybody see this? Here, for example, there's this green, is a yellow facing a yellow across here, right? There's the yellow, the underneath of the green saddle is yellow and it's facing a yellow saddle there, right? You have yellow facing yellow here. Everywhere yellow is facing yellow. So I can push the yellows together, right? And I can push them right through the greens so that I end up with two greens facing each other. Okay, so these the way the surface is arranged, there's two yellows are facing. There's going to be a sort of a middle point where the two saddles collapse. The two saddles. So here's the two saddles form just one saddle. Here's the four arms of the saddle. And how does it look? Well, this arm connects around to here. Right, and this arm turns around, goes out here, makes a loop, and connects to this one. Okay, so here you have an intersection, and here you have an intersection. Okay, so at the midpoint of going from here to here, right, the yellow and the green coincide exactly, and they coincide along this particular surface. If you check this, this is a punctured mobius strip. This is a non-orientable. Right, this is a non-orientable thing, but this is just this doesn't really exist in the process, because what's happening is you just have the two parts of the surface are at one point they're just going past through each other, and if you were to freeze the process at that moment, what you would see is this punctured mobius strip, but it's actually two copies of this thing superimposed, and then they push apart on the other side, and the yellow, now you see the yellow on top, and you have two greens facing everywhere. So before you had two yellows facing, and afterwards you have two greens facing. Okay, so now what do we do? Well, think of what's happened. We started with, this was a yellow sphere, remember? A yellow sphere, and we sort of pushed out this green blob and deformed it. And then we started twisting, and we got to this thing here. And then we pushed the layers one through the other, and we got something that looks exactly like it, except with colors reversed. So all we have to do is undo all those steps we did before. I'm not going to do it. We undo all the steps we did before, and we get to the same thing colored yellow. Right, so that's how you turn the gizmo inside out. That's really the maneuver I wanted to show you. There's a lot of mathematics setting the context for this this sort of very kind of geometric. It's like kind of claymation. This step-by-step deformation. But this is really the key to the inversion. Is the rotation. Let me just mention that here. you go from here to here, you rotate the green 180 degrees clockwise, counterclockwise, excuse me, as we did it, as you saw it, right? Now to go backwards, you have to rotate the yellow 180 degrees in the opposite way, right? Because I'm undoing the process, right? But that means that relatively, the green has rotated 360 degrees with respect to the yellow. So I said this before, that in every inversion scheme, there has to be a 360 degree rotation of one element with respect to another. And that's why it's so much work, because you have to put the sphere into a configuration where you can actually rotate part of it 360 degrees with respect to the other. Anybody have a question? If not, if there are no questions about what we saw here, I'll just go back and tell you a little bit about the mathematical background that I said I was going to skip. These are all the steps. So we're looking at ways of going from the sphere into 3 space. Right, this process is a manipulation of the sphere in 3 space. Well, the way to formalize it mathematically is we think of it as a function f from the 2 sphere into R3. And you can think of the 2 sphere as sitting in R3 itself to start with, right? The usual 2 sphere, and it has coordinates. You can use spherical coordinates, say, you can take the unit sphere and then use like spherical coordinates phi and theta, or locally you can use whatever coordinate system you like. And I'm just calling it, say, UV up here. So that would be a coordinate patch on the 2 sphere that you're using to describe your function explicitly. Now, the function is going into 3 space, so it has 3 components, f sub x, f sub y, and f sub z. Okay, so each point, a point, say P, on the on the sphere is going to go to a point P in 3 space with its its 3 coordinates with respect to the axes in why didn't have that? That's do better than that. Anyway, the 3 coordinates with respect to the axes in 3 space. Sorry for my geometry here. Okay, so if this is the point UV, then this would be f sub x of UV, this would be f sub y of UV, and this would be f sub z of UV. Now the condition we want, we say that f is an immersion if this matrix so it's an immersion if and only if this matrix has rank 2 everywhere. So rank 2 just means that it's a 1-to-1 map locally. If you have a little piece of the sphere here, it's going to map to a little nice piece of surface in three-dimensional space, right? If you had a, in particular, let's see, what does this picture mean? I guess this was, where are we? Yeah. So this is going to be, I have a little piece. So this is a coordinate chart on the sphere. I have a little piece of the sphere, and F takes it to some nice little piece of surface in three space. So locally, you don't have any self-intersections at all. You just have a nice little piece going to a nice little piece, right? If you, you can always avoid the self-intersections locally. And the rank, one good way of thinking of the rank condition is to understand rank condition. It means that if I have any curve on the sphere with non-zero tangent vector, so you have any curve, like some nice curve like this with non-zero tangent vector on the sphere. So here it is, right? It gets transformed to, it gets, when I compose it with F, it goes to such a curve in R3. So if my original curve on the sphere had non-zero tangent vectors anywhere, everywhere, then the image under F of that curve will be a curve in three space with non-zero tangent vectors. So it means that, for example, you can't have a cusp like this, because when the curve went through the cusp, right, the tangent vector along this line, right, would have to, it would kill the tangent vector as you pass through that line. So that's the explanation of what an immersion is. And the theorem I was mentioning, let's just get a couple of, whoops. Oh no. Yeah, here we go. I don't know why this happens. Just give myself a couple of pages. So the one reason why everyone thought this was impossible in fact, the fact that the version existed was proved by Stephen Smale, who went on to win the Fields Medal for other achievements around, I think maybe 1958 or something like that. So quite a while ago. And at the time, his advisor, the story is at least that his advisor was another very distinguished guy, Raoul Bott, told him that can't work. There has to be a mistake in your thesis, because it would imply that you could turn the sphere inside out, and we all know that's impossible. And one reason people thought it was impossible, that if you go down one dimension, and you look at maps from the one sphere into R2. Now the one sphere, so these are maps of the circle into the plane. Okay, so you can think of the unit circle with the coordinates, say t. T is, say, going from 0 to 2 pi, right? And as you go along the circle, you have this map F, which is mapping the circle into the plane. And the condition, the immersion condition, is just that the vector f prime of t, right, this is, F is a vector, it has two components. the vector f prime of t is never zero. Never has a zero derivative. So for example, the standard immersion would be t goes to say cosine t sine t. Right, if you do that, then if you just take t as I suggested up here, it's kind of a linear parameter along a line, t varying from 0 to 2 pi, t goes to cosine t sine t, wraps the circle once around like this in this direction. And if the derivative, so this would be f of t, and f prime of t is the vector minus sine t cosine t. And this vector has length 1 always, right? Because sine squared t plus cosine squared t is equal to 1. So that's certainly an immersion. Okay, let me get another piece of paper here. Yeah, so the standard would be f of t equals cosine t sine t. But I could also take, for example, g of t equals minus cosine t sine t. Right? If you calculate the derivative of this, the squares of the two components add up to 1 again, and this map here minus cosine t sine t goes around, but in the opposite direction. So let's see, this is my x and this is my y. So let me do it as cosine t minus sine t to give my mind a break. So instead of going around like this, we go around like this. We go along the same track, but in the clockwise direction instead of counterclockwise. Now, the theorem of Whitney-Graustein says that let's call this a non-singular curve, or an immersion, a closed non-singular curve is determined by its winding number. Now, this doesn't make complete sense as I said it. So it's not the curve itself, it's the class is determined, let me interrupt here, up to deformation through such curves. It's determined by its winding number. I'll tell you what the winding number is in a minute. But what this says is that two curves, you can get from one to the other through a deformation, through a one parameter family of closed non-singular curves, if and only if they both have the same winding number. And the winding number is defined this way. You have a curve that has a non-zero tangent vector everywhere, right? And you look at the, so this is f of t. And let's suppose I go around the curve at unit length, at unit speed, so that the tangent vector always has length 1. So in that case, I have another map, f prime of t, which takes every point from 0 to 2 pi to a point in the unit circle, right? So for example, here, I start out at this vector. So I would start at this point here. Then I turn, so I would go around to this point, and I keep going around, right? So I'm down here, right? No, I'm saying this wrong, right? I started at this point. I'm at this point, which is here. Then I get to this point, which is here. So I go all the way around. Then I come back. So what is the winding number of this curve? The one I drew. Can anybody figure this out? Hey, May Rose. Good to see you.
Good to see you too, Professor.
Thank you. You can just do it with your hand, right? Imagine you're going around, right? You go back. How many times is your hand turned around as you traverse the whole extent of the curve?
I did it with my hand. It's one time.
Once?
Yes.
Does everybody agree?
Yeah, I agree.
Yeah. Okay. Here's another one. Say, let's imagine we're going in this direction. Anybody figure this out? I mean, it's not very hard, right? Just take a pencil and imagine going around the curve and just calculate how many times your pencil is turned around.
I think it's a one time as well.
It's one also, right? So this curve and the curve that just goes around once like this, there should be a deformation between this one and that one. Now you can't just pull out the loops and get something that looks like this, right? That would be very economical, but you're not allowed to do that because this curve here would have non-zero tangent vector at these 2 points, right? So how can you do it? If you have paper and pencil, you can just experiment. Anybody figure out how to do this? It's the theorem that says you have to be able to do it. down to 4 people. That's really unfair. I'm putting a lot of pressure on you. Well, let me leave that as an exercise for you guys to think about. And if you work on it for a week and you can't figure it out, get back in touch with me. But it shouldn't be that hard. You just have to experiment a little bit with sliding the curve around to put it in a position where it's clear how to move it to make the two regular, deformable one to the other.
Oh, I think I have it.
Okay, who's talking?
Admin.
Okay, Ajman.
Could I share screen?
Sure.
So this is Microsoft Paint. So this is the original curve, right?
Yeah.
All I did here was to take this edge here and
Mhm.
pull it over the loop. So then the edge comes here.
Right.
Right.
There you go.
So now this edge has become this edge. And then now the last thing you have to do is just you want to take this edge, or let me take another color, orange, and I want to push this out like here. So then what you'd get is just, if I take this loop and pull it through that way,
Right.
So I'm pulling it out this way.
Right.
What I'd get is just a circle, right?
Right.
Okay. So
Yeah.
yeah.
But notice that you have to get from one of these to the other, you have to go through a triple point, right? You can't, there's no, you have to actually, I mean, again, this just tells you that they're a little bit far apart in the space of regular curves in the plane. In order to get from, even though they're in the same deformation class, to get from one to the other, you have to actually travel some distance in the space of curves, go through a triple point singularity, and then you can get to the other one, right? You can't resolve it easily without the triple point, which would be in the middle where that brown arrow is. Yeah. Thank you very much. So Ajman, that's all I have to say for today. If any of you people want to get in touch with me, I'm I still have my regular Stony Brook email, and it's where do we go? Let's see if I want to share a screen. Share. It's oh, come on. Screen mirroring, connect. There we go. What's happening here? Well, I can see my screen, but I can't do anything to the screen. It's gone all fuzzy. Anyway, it's tony@math.stonybrook.edu. So any questions about this? You want to do more reading in this direction, just let me know. I'll be happy to talk to you. But that's it for today.
Thank you so much.
My pleasure. What happened here? Well, I'm I'm new to this equipment. Okay, I don't even know how to stop. Oh, stop the share. There we go. Okay, guys, so I'm leaving, but nice to see you.
Bye.
Thank you. Have a good night.
Sign up for eBoard, please.
Did already.
I know you did.
Are we having another social on Saturday?
Yes.
Do you have any
Maybe-
suggestions what to do for that?
No.
Yeah, Mark won't be there, so we can't use Mark's brother's Jackbox account.
Yeah, how was that? I wasn't there when Mark did that.
It was fun. It worked out really well, I think.
I liked it.
Okay. Yeah, maybe Spencer's not here, but yeah. All right. I think the recording will end once the meeting ends anyway. So I'm gonna go. You guys can, if you want to stick around, you can. But I'll be
I might
gone.
also go.
Okay. Bye.
Okay.
Bye.